I'm also going to post this recording later today whenever they become available. So let's just go ahead and get started. So I will send this out to you as well if you're interested in seeing it, reviewing it on your own. But I wanted to talk about the recitation activity that we did last week. I kept seeing a lot of common mistakes that I think that are worth addressing before we go too much further. First of all, can you all see what I'm sharing right now?
Yes.
Okay, good. So just to remind you all, we started off with these two acceleration expressions, and our primary goal was to get closed form expressions for the velocity of each car as well as the distance traveled by each car. So open form, I think most people did a pretty good job with. So you knew that to find the net accumulation, let's just stick with V1 here. To find the net accumulation of the changes in velocity, you need to integrate from 0 to t of your acceleration function. And then, so that's your net accumulation. To get the velocity at any time for that car, you need to have the net accumulation at any time plus the initial velocity of that car. So that's the way you build both the open form velocities, and the way that you build both of the open form distances is very similar. So I didn't see that most people had a big problem with that. The errors that I was seeing that were pretty widespread happened when we start working on the closed form. So I just want to walk through velocity 1, and then I'll email this PDF out tonight so you can take a look at it. But I go through in detail velocity 2 and the two distance expressions in closed form as well. So again, velocity 1 in open form, rather than just, I think we spent most of the semester on using GC to interpret these things and graph them. Now we actually want to do this by hand. So we're going to drop in place of A1 of U du, we're going to drop in our function here, and I already see a problem with it. I should not have t's in my variables. I should have u's there, but we'll just move past it for now. One thing we know that velocity 1 of t is going to be equal to velocity 1 of 0 plus this integral. I think it was given very early on that the initial velocity of that car is 2.5 meters per second. So now we have, now we need to take this antiderivative. So we've been doing so many techniques for these. So hopefully, both of these terms, the way you handle them using anti-differentiation are pretty comfortable for you now, especially this first one. So this is just power rule 0.7t. So increase the power by 1, divide by 2. We have a simple case of undoing the chain rule to get from this sine to this cosine function here. And again, even for most of this, I was seeing a lot of correct work. It's what happens from this point forward that I start to see people making dangerous assumptions. So we've taken the integral, the antiderivative, but now what we need to do to finish the integral is evaluate it at both of these limits. So when u equals 0 and when u equals t. So most people are okay with doing the upper limit. It's what happens when we need to evaluate it at 0 that I saw some things that concerned me. So plugging in t, you get this expression here. So really nothing changes. You just change your variable from u to t. Plugging in 0, I think that there were quite a few people who took the assumption that, all right, if I plug in 0, then all of this stuff is going to vanish. which is true for one of these terms, but is not true for the other. So just to kind of stress it again, don't ever take that 0 for granted. Plug in the 0 and make sure the terms actually do vanish, because not all of them will. In fact, in this case, cosine of 0 is 1. So this second term ends up being negative 5 over 3 pi. So because of that, once I clean up everything and simplify, I get this expression for velocity of 1 of t that has these 4 terms in it. Which brings me to the next thing I wanted to bring up that I see people making assumptions on. By now, I believe all of you know that when you integrate, you're going to have a constant of integration. A lot of people are still assuming that that constant of integration is equal to whatever the initial value of my function is. So I saw a lot of papers when I was grading this that said, all right, c is equal to 2.5, because that is the initial value of that function. And you can't quite do that because, okay, let's say I just left off this 5 over 3 pi term. If I plug in 0 for time here, this term right here is going to go to 0, but this term right here is going to give me a negative 5 over 3 pi, which is why I have to have a positive 5 over 3 pi to really make that velocity, that my initial velocity stand out and be correct. Any questions on that before we move on? Okay, like I said, I mean, there's obviously 3 more functions you all had to deal with, so I'll send this out so you can take a look at it, but I really wanted to focus on V1 because that's where I saw the majority of the mistakes. All right, so keeping on that same line, I'm going to go ahead and share from my iPad now. So what if we had something like this? So I'm going to give you something in the open form. I keep doing this mistake. So I'm going to give you a few minutes to take a look at this. When I come back, I want to see a closed form expression for this integral here. All right, so go ahead and take a couple of minutes, then I'll check on you in just a bit. All right, how do we start this one off?
Is this chain rule?
Yep, we're going to use chain rule here. So what tipped you off that we need to use chain rule for this?
There's an equation enwrapped inside of the sine function.
Yeah, so yeah, we have an inner function here. We have a composite function. We're going to use chain rule. So what would this antiderivative be, knowing we have to undo the chain rule?
Would it be -1/2 cosine 2t?
How do we feel about that, everyone?
I think so.
Okay. So now we need to evaluate that at x and 0. What happens when I continue from there? I guess I should keep this separate. So when I evaluate it at the limits, what do I get?
At 0, you get -1/2.
Okay, so at 0, we get -1/2. How about when we plug in x?
-1/2 cosine 2x.
Okay, -1/2 cosine 2x. Something like that?
Yeah.
Anybody see any problems? So yeah, so I see in the chat here, it should be +1/2. Remember when you make sure you're subtracting what you're actually given here. So yes, I do subtract, but when I plug in 0 for t, I get -1/2 from that cosine function. So if I do some cleaning up here, I should get something like this: 4 plus 1/2 minus 1/2 cosine 2x, or 9/2 minus 1/2 cosine 2x. How do we feel about that?
I'm sorry, I was writing. Why did we add 1/2?
So when to go from this step to this step here, so we have to do two things, and let me give some space and
So I'm confused where the 9/2 came from.
just 4 plus 1/2.
Oh, I see now. Okay, right.
So remember, when you're evaluating a definite integral like this, when you have limits of integration, you have to evaluate it at the upper limit, then evaluate it at the lower limit, and then subtract those two things.
Great.
So this guy right here becomes 1. So I have, minus a -1/2 comes out to +1/2.
Oh, gotcha. Okay.
Cool.
Thanks.
Good question. Anything else about this one before we go on? Okay, so like I said, I wanted most of this time to be for you all to ask the questions that were important to you. So just what the things that are going to be on the test on Friday are going to be primarily all the physics applications that we did with accumulation functions and integration. And then most of what we spent in the last 2+ weeks on is anti-differentiation techniques. So undoing product rule, undoing chain rule, partial fractions, all the trig manipulations that you have to use identities to process. There are a lot of examples on Canvas in that folder entitled Exam Preparation Materials. So I'll just open it up to you. What What's important? What do we need to discuss? What do we need to really review between now and Friday?
Can we go over some of the physics applications again? Because those were so long ago, I don't think I quite remember.
Sure. So the most prevalent physics thing we've talked about is work. Would it be agreeable to look at the one that he assigned recently?
Yeah, that'd be good.
Okay, so I'll go ahead and open that and if you'd like, I can send this solution out as well.
That would be great.
Okay, yeah, I'll send this PDF out as well. So let's just go back to the very beginning. We want to find the work done. How do you find work done in a situation? A very simple formula for it.
You take the integral of the force equation.
Okay, I'm thinking even simpler than that. So you're taking the
Force
integral of
times
force.
distance.
Yeah, just force times distance, right? So now if we get integration involved from there. So, and I think hopefully by now you've noticed that when you're doing an integration, when you're using an integral to accumulate any quantity, volume, area, whatever, the most important part of this process is getting the correct rate of change function. So let's talk about this first. We know work is force times distance. What does the rate of change function look like when you are finding work? Like, what is the rate of change function actually measuring?
It's force, right?
Yeah, it's just force. So typically what we do is we have a rate of change that's given in, it basically just measures force. So it's given in newtons or pounds. And the integral itself, like the independent variable for the integral will be your distance. So in this case here, we're lifting something off the ground. So the force that we're concerned with is going to be the force of gravity. It's going to be the weight. So just to kind of refresh your memories, I think this was assigned about a week ago. Basically, you have a bucket on the ground, and the bucket has some water in it, and you're going to be lifting that to a height of 35 feet. So basically, I'm concerned with the different weights at play. So I have three objects whose weights I have to worry about: the rope, the bucket, and the water inside the bucket. So basically the way that I work through this, and I'm showing this to you basically as one way to organize it, but I saw a lot of valid solutions that got to the correct answer that were not done like this.
Are you sharing a different screen because we still see your notepad from the last question?
Oh, you do? Okay, let me correct that. Oh yeah, I never shared from my laptop. So nothing I was saying made any sense, right? Does it seem more relevant now?
Yeah, not really.
Okay.
Sorry. All right. Yeah, that's better.
Okay, good. All right, so a lot of the stuff we said before is still true. Rate of change of a work function is solely concerned with force. So we're lifting something off the ground. Weight is the force we care about. I care about the weights of these three objects, and basically I'm just going to find the weights of those three things individually and then add them up. So the rope, the water, and the bucket all have weights. Let's just start with the bucket because the weight of the bucket is constant. The bucket weighs 8 pounds, so I've called that here W sub B. Bucket's really easy. I just know I have to add 8 to whatever I find for the rope and the water. The rope, I believe we are told that the rope has a total weight of 32 pounds and that it's 50 feet long. So I can use that. I can use that information to find out that for any length of this rope, I can just multiply 0.64 times that length of rope, and I can get that weight. So I have a constant rate of change of the weight of the rope with respect to its length. From there, I know I'm building a linear function for the weight of the rope. So I think by now, you probably all have your favorite method for coming up with the equation of a straight line. And that's basically all I've done here. So when the height is 0, the weight of the rope is going to be, 35 feet of that rope times 0.64 pounds per feet. So the heaviest the rope is going to be is 22.4 pounds. When I have this bucket 35 feet off the ground, there's going to be no rope remaining, so it's going to be weightless. It's going to have a weight of 0 pounds. So based on those 2 points, I can write this linear function here, 22.4 minus 0.64 h. Any questions on that before I go on to the water one? The way I develop these is very similar. All right, so same kind of idea with the water. You are told that at the bottom, the bucket is holding 19 gallons of water. At the top, it's holding 12. And you're also told that water spills out of it at a constant rate, so a linear rate. You're also given a conversion factor to convert from gallons to pounds. So I know the initial weight is 157.7 pounds. Final weight is 99.6 pounds, which gives me a slope of negative 1.66 pounds per foot. And then I can use that to build my linear function here. 157.7 minus 1.66 h. So now I have the weight of the rope for any height, the weight of the water at any height, and even though it's really simple, the weight of the bucket at any height. Which means I can add those three together and get myself a total weight regardless of the height, or sorry, with respect to any height. And that comes out to 188.1 minus 2.3 h. So again, the most important part of this is the rate of change function. So any questions about how I got to this f of h function? Oh yeah, from there, once you have the rate of change function, then to find the work, you just integrate that over an appropriate interval. So 0 to h is going to give me this, is going to give me the function that tells me what the work done is over any interval from 0 to height. But if I want to find the entire work done, I just plug in 35 for h, and I get this final number here, 5,174.75 foot-pounds. So any questions on the way that I did this? And hopefully by now, I mean, I did this integral by hand, but I think this was, he covered this material when he was still, using GC for a lot of this stuff. But hopefully by now you can use anti-differentiation on a product rule example pretty quickly now. Anything else to talk about with this example here? All right, that was a good question. Anybody else? What should we talk about? So if nobody has any specific questions they want to ask, I think what we should do is talk about some of the anti-differentiation techniques, because those are going to be a big deal on Friday.
Yeah, I actually had a question on one from the iMath. I just didn't know if you could see it or help us with something similar to it.
Yeah, we can. Well, I have no problem talking about iMath problems.
Yeah, it was just very odd because it was a very specific problem. I know how to undo the product. Wait, actually, I think it was decomposition, partial fractions.
Okay.
Yeah.
I'm going to share my screen from the iPad again.
Okay.
If you want to just tell me the function, we can go through it.
I know the top was like x cubed plus 33, and I think the bottom was x squared plus 4x plus 3. Which
Okay,
I
that sounds
think-
familiar actually.
Yeah.
All right, so x cubed plus 33
Yep.
over x squared plus 4x plus 3.
Yes.
All right, and we'll integrate this. All right, so what is the first thing that I must do for this thing?
Factor the denominator.
Okay, we can factor the denominator. So x cubed plus 33. What does the denominator factor into?
X plus 1 and x plus 3.
Okay. Okay, that's a good first step. Where do we go from here?
Could you split it into its separate parts, right?
So we're jumping the gun a little bit. There's something that we should do before we
Wouldn't we divide polynomials because the numerator has a greater degree than the denominator?
that's exactly it. So when you're looking at partial fractions, if you ever have the degree of the numerator at least as large as the degree of the denominator, you want to do a division step first,
Gotcha. Okay.
which is probably what caused you some problems here. So I'm going to divide x squared plus 4x plus 3 into x cubed plus 0x squared. Make sure to put all your placeholders in, but I think by now I haven't seen that tripping up too many people. So let's just fast forward a little bit. I don't think this is the part that's causing people most of the heartache. On the other hand, if I am making a mistake, someone please catch me. But this looks familiar. So there's the long division. So what does that tell me that my integral needs to be transformed into? How do I need to rewrite this this integral?
Don't you write it as like the 13x plus 45 over the like the factored denominator, and then you just put the x minus 4 on the outside?
I don't want to put it on the outside, but did you mean outside the integral or just outside the?
Outside of the fraction.
Okay, good. So yes, 13x plus 45. And we've already factored, so we might as well use it. And I saw a question in the chat. Is there a shortcut for the long division part? Unfortunately, not really. So I know a lot of you probably remember how to do synthetic division from prior classes. The problem with synthetic division is it does not work for divisors like this. And also, I mean, I don't really, personally speaking, I never use synthetic division just because I just don't really care for it. But unfortunately, the only way to do the long division faster is just to get more comfortable with it. But me doing it right there, that was me working through this the fastest way I knew how. I do not know of a good shortcut for that polynomial long division process. All right, so I think we could probably easily integrate x and -4. So we'll just leave those for the end. What am I going to do with this this rational function here?
Now you're going to do partial fractions.
Okay, so I got 13x plus 45 over x plus 1, x plus 3. And what would the framework of this thing be? Like what's my next step going to look like?
The integral of a over x plus 1 plus the integral of b over x plus 3.
Okay, and if you all agree to it, I'm just gonna ignore all the integration stuff till I get done with this. and then I'll integrate everything together. But for right now, all I'm doing is splitting up a fraction. All right, so from here, this is a good start to this process. What should I do next?
Multiply a times x plus 3 and b times x plus 1.
Okay. Is that what you meant? So really what we're doing in this process is really, I'm just trying to clear all the denominators at once. So I'm going to multiply both sides by x plus 1, x plus 3. And what that allows me to do is, all right, all these denominators go away. This cancels this cancels this. So I'm left with 13x plus 45 equals a times x plus 3 plus b times x plus 1. All right, so it definitely looks a lot friendlier. Now what?
Combine like terms and set equal to the denominator.
Okay. So 13x plus 45 equals ax plus 3a plus bx plus b. If I start collecting things, my x terms are a plus b. My constants are 3a plus b. So what does that tell me then about where can I go from here?
You set the corresponding coefficients equal to one another.
Okay, so a plus b equals what?
Uh, 45?
Not quite. So,
Sorry, I usually distribute it and then look for the x's. So
oh, okay. So let me do that on the other side here. And then I'll talk about why I wrote it the way I did. So yeah, we already distributed it. So our x terms are going to come from ax and bx. So I know that ax plus bx has to equal 13x,
yes.
or a plus b equals 13. And then for a similar reason, 3a plus b has to equal 45. So the reason I did this step right here, and this is not something you have to do, it just kind of the way I've gotten used to doing it. Sometimes these examples have a lot more powers of x than just linear and constant. So I just think it's easier to just group them together like this to see that, all right, my x squared terms are really going to be these coefficients.
Makes sense.
All right, so now I got two equations, two unknowns. It's just, I think I have an idea where I would go next, but how would you handle these two equations, this system of equations?
I would do elimination with the top equation.
Okay. So, oh, what do you mean by that with the top equation?
I would put a -1 in front of the top equation.
Oh, okay, I got you.
Your b's cancel out.
All right, so that's going to give me 2a plus 0 equals 32, which means a is equal to 16. And then from there, we can say that b is equal to -3. Feel good about that? So now I can really do my integral. So that was 16 over x plus 1 minus 3 over x plus 3. All right, so now we have four much simpler terms than what we started with. So let's just take them piece by piece. What's the integral of x?
X squared over 2.
X squared over 2. -4.
-4x.
Yep. All right, and then the next two are going to be The most complicated, but still not too bad. What's the integral of 16 over x plus 1?
16 natural log absolute value of x plus 1.
Okay.
Oh,
And similarly, minus 3 natural log x plus 3.
I think I typed mine in wrong then.
Okay. One thing that I'm noticing is I've make sure you use ln instead of log, and it is picky about the absolute values.
Okay.
Another thing to keep an eye out for on iMath is that it if you have unmatched parentheses, it can be pretty hard to track those things down.
I know. Oh my gosh, it's a
Yeah.
nightmare.
Any more questions on this example?
Thank you for going through it.
Yeah, no problem. I think the partial fraction thing is a valuable thing to look at before Friday.
I kind of have a question. This might sound weird, but use substitution when you have like a square root in the denominator.
Okay.
I've seen that they usually make the whole square root like the u, and I
All
just want to go through an example of that.
Yeah. Do you have a specific one, or do you want me to just invent one?
I have one from the iMath. I have another one if you don't want to do that one though.
No, let's do iMath. We can do iMath ones. That's fine.
Okay, yeah, it's just x over the square root of x plus 2.
Okay. All right. So yeah, this is, I don't see a way to do this the way it looks right now. So you mentioned u substitution.
Yes.
What would u be equal to?
Based on what online does, it would be the whole denominator.
So square root of x plus 2?
Yeah, I don't know. That's where I get confused.
Okay, so let's follow this train of logic. So we have a u, which is going to be radical x plus 2. But it's not just the x's we're trying to transform in this integral. It is also dx,
Right.
which means we have to deal with the derivative of u as well. So what would the derivative, what would du dx be?
Well, the derivative of u would be u squared over 2.
Um,
I'm sorry, I'm not super comfortable with this.
I would, if I may,
yeah,
Yeah.
go ahead.
I would set the equation to like the exponent of -1/2, and then I would just do like the rule for functions.
So you have x over x plus 2 to the negative, or to the 1/2.
No. So in the du dx, like I would, before doing that, make it -1/2 instead of the square root. I mean,
Okay. Well, it would, so this one would be positive 1/2.
okay, because yeah, we're dealing with it out of the denominator. And then I would do 1/2 times x plus 2 to the -1/2.
Okay.
One. Oh yeah, times 1, whatever. Doesn't matter.
Yeah, well, yeah, you do need to worry about chain rule, but the derivative of the inside is going to be 1. All right, so from here, so let's just rewrite one more time. That would give me 1 over 2 radical x plus 2, which is equal to 1 over 2u. So I have du dx equals 1 over 2u, which means if I cross multiply, I'll get dx equals 2u du. Does it make sense how I built all those pieces up?
Sorry, I want to let whoever asked the question get it.
So
Yeah,
I'm going to start dropping things in. So dx is just going to be 2u du. Radical x plus 2 is going to be u. But what goes on top, what goes in the numerator of this fraction?
Would you have to solve for x in terms of u?
Yeah, let's try that. So u equals radical x plus 2. That gives me u squared equals x plus 2. And x equals u squared minus 2. So I have u squared minus 2 times 2u du. So those cancel out. So I end up getting the integral of 2u squared minus 4 du, right?
Yep.
Okay. I'm actually kind of surprised with this because I did not think this was going to work. So let me show you a simpler way to get at this. So it's pretty similar, but instead of having u equal to radical x plus 2, I'm going to have u equal x plus 2.
Okay, that was my like initial thought, but then when I was going to look it up online, they did the square root. So that's where I got confused.
Right. So, and my intent was to go through the square root process and show you that it wouldn't work. I'm actually surprised that we can get to the same place, but this is going to be a lot simpler. So du dx is just going to be 1, right? The derivative of x plus 2?
Yeah.
Okay. Which means du and dx are the same. So from there, I can start dropping in these things. So if u equals x plus 2, that means x equals u minus 2.
Right.
So then this becomes u minus 2 over the square root of u du. And from here, what can we do?
I'm sorry, did you find the dx?
Well, yeah, dx is equal to du.
Oh,
So I can exchange one for the other for free.
shouldn't you just find, well, what I usually do in like in my steps is just find the integral of that with u. I would do the square root, so I'm not really sure.
So there's one more thing we can do here that makes it pretty simple. So I'm going to do the integral of u minus 2 and rewrite this as an exponent. And if I do that, that opens this up for me, or at least makes it a little more obvious this is the case. So I can just divide u by u to the 1/2 and get u to the 1/2. And divide negative 2 divided by u to the 1/2 and get minus 2u to the negative 1/2. Does it make sense how I did that?
Yeah.
Okay. From there, I think this was the intent, because this integral right here is pretty simple. Like, not this one right here is pretty simple, but I felt like it took a lot longer to get there. So this one right here, what is the integral of u to the 1/2?
Two-thirds u to the 3/2.
2/3 u to the 3/2. And how about the other term? How about that? No, I already don't like it. Do y'all agree with me?
Yeah.
Okay. All right. Are we done?
No, you have to resubstitute.
Yep. So do 2/3 times x plus 2 to the 3/2. minus 4 times the square root of x plus 2 plus c. And let's just really drive the point home that either way would have worked here. So if I did the integral of u squared minus 2 du, oh no, it's 2u squared minus 4. If you distribute that 2, then you get 2/3 u cubed minus 4u plus c. But in our first attempt, what was u equal to?
The square root of x plus 2.
Right. So that actually is going to come out to the same thing. 2/3 times x plus 2 to the third, but to the 1/2 power, minus 4 times the square root of x plus 2 minus c.
Right,
So,
but the algebra is easier the second way.
Yeah, absolutely. But just to kind of put your minds at ease that if you do something that's not the best approach, as long as you do all the math correctly, you're going to be fine. Any questions about this example here? The u substitution stuff, which I think is the newest thing he went over, right? All right, I have 3 minutes left. I'm going to go ahead and make sure the quiz is open for you all. And I will stay in the room for a little while if you have any questions. Any last minute things before we wrap up?